Okay, so just a recap of chapter 8. We talked about the sampling, the distribution of the sample means. So basically, we just dealt with one important formula, and that is we converted the sample mean into a z-score using this formula. All right. So we looked at the distance between a sample mean and the population mean, and we call that the sampling error, and converted that distance into a standardized z-score where we divided the sampling error by what we call the sampling error of the mean. All right. In other words, we simply computed the standard deviation of all the x bars. So this is the definition of the sampling error of the mean.
I have a quick question.
Sure.
Is the sampling error of the mean the same as the standard error of the mean?
It's also, yep, it's also the same as that. Can also standard error. This is probably the more appropriate. Thank you, Doug. This is the more appropriate term there. Standard error of the mean. Okay. So we use this formula if sigma is known. If sigma is known. As we will see in chapter 9, there will be instances where the population standard deviation will not be known, such that we will compute, instead of the z-score, we can convert the distance of x bar from mu in terms of, and then here the standard error of the mean will be computed as S, which is the sample standard deviation, divided by the square root of n. Okay? So again, when sigma is unknown, and there will be many such instances, that we will be using the sample standard deviation in place of the population standard deviation. Now, recall too that in chapter 8, we will introduce to the central limit theorem, right? And a couple of important bullet points that we talked about was that regardless of the original distribution where a sample is drawn from, that as the sample size increases, okay, from 2 to 3 to 4 and so on and so forth, the distribution of x bar will become more bell-shaped. That for symmetric distributions, the requirement is, and the sample size must be at least 10. But for distributions that are skewed, what's the requirement? What's the sample size requirement for x bar to follow the Bell distribution? Does anybody remember?
Is it 30?
Uh-huh. Okay. So keep this in mind, because when we compute confidence intervals, especially for the population mean, when the population standard deviation is not known, you can use the formula that uses the t-distribution for computing confidence intervals. Okay, this concept here will be carried on to chapter 9. So here's an important worksheet that I would like you to pay attention to in chapter 9, the Excel file that is available in Moodle. So Note that this chapter involves computing confidence interval estimates for unknown unknown population parameter. In other words, let's say that you are doing a market study of, say, the city of Ashland, and an important statistic that you need to have in that market study is knowing, say, the actual average, say, household income of, say, the folks living in Ashland. All right. So, if you are interested in knowing what the true annual household income of Ashlanders, you can do some research, maybe look at the statistical abstracts of the United States, or maybe do see if you can find, in the Ashland Chamber of Commerce, and see if they have this information available. Okay, because sometimes you really don't need to estimate this number, especially if someone or some group or organization has already done the work for you. But in many cases, maybe the statistical abstract of the US may provide this kind of information, but sometimes they do it every 10 years. That may be the last information you have available was from 10 years ago, which may be at this point obsolete. So what do? Well, in your case, if this is an important information that you need to have in your market study, then you will try to provide an estimate of this unknown actual average of household incomes of Ashlanders by way of taking a sample. All right. Later on in this chapter, we will talk about ways of estimating the sample size requirement. In fact, at the bottom of this worksheet, you see this down here? You'll see that there are formulas that you can use to compute the minimum sample size. So a sample size is, many people have a misunderstanding of the minimum sample size requirement, and they usually cite this 30. Well, that's not really true, okay? This number here simply pertains to the central limit theorem that talks about the distribution of X bar. So if you were doing a research study that you are trying to estimate an unknown population parameter, such as the mean or true proportion, you're estimating an unknown mean or unknown population proportion, you can rely on these two formulas for computing the minimum sample size requirement. So towards the end of this chapter, we will have one or two examples that show how you can compute the minimum sample size for estimating either the mean or a proportion. Okay, so let me go back to this example. So we'll go back and say we need to estimate the true mean or the true average annual household incomes of Ashlanders. If this information is not available or is obsolete, then we can rely on sampling, where from a sample we compute X bar. Okay, X bar is a point estimate. So X bar is a point estimate of mu, in as much as P, sample proportion, is a point estimate of true population proportion. Okay, so in a previous session, we talked about X bar and P as we call this as point estimates. Okay, it's a single number that is used to estimate an unknown population parameter. But in estimation, we don't necessarily rely on point estimate only, but rather what we do in estimation is we compute what is known as a confidence interval estimate. Okay, an interval estimate. So an interval estimate is where you add to the point estimate, you add or subtract what is known as a margin of error. Okay, so for example, I want to say, hey, you know what? I computed X bar as $50,000, give or take, or plus or minus, say $5,000. So if you added the $5,000 to the 50,000, you get what is known as an upper. So if you added point estimate to the error, you have what is known an upper limit. If you subtracted the margin of error from the point estimate, you have what is known as a lower limit. Okay? Now, this chapter talks about this interval estimate where we say, we add this word confidence interval estimate because when we make interval estimates, we would normally want to attach a certain level of confidence to that estimate. All right, this level of confidence could be 90%, 95%, 99%. So depending on how high confidence you would want to attach to your estimate. All right. Okay. So using this chart here, if the problem is asking you to compute a population mean, all right, this over here. So based on how you read the problem would ask either to estimate a mean or a proportion. If the parameter of interest is estimating a population mean, then we follow this flow chart that says, all right, first question that you ask yourself is this: is the population standard deviation given, or is it stated in the problem? If the answer is yes, you follow this path here. If the answer is yes, you go down, it says you will be using the Z distribution. All right. Now, this using the Z distribution assumes, you will have to assume that the sample is coming from a normal distribution if n is less than 30. So here's the formula that you will see for estimating an unknown population mean. You have X bar, which is the point estimate, and then which I covered the give or take. Let me erase that so you still see the plus or minus. Okay, so that's the point estimate over here, and this whole part here is the margin of error. So we'll just call that E, or you can say ME. All right. So note that in this formula, X bar plus or minus Z times sigma over square root of n, that the margin of error, E, is composed of these three things: Z, sigma over the square root of n. Okay, I just rewrote this equation here into this more readable form. Obviously, if you are trying to estimate an unknown number, you would want two things, right? One is you want your confidence on the interval estimate to be as high as possible, maybe 99%. Secondly, you would want the margin of error as small as possible. Okay, meaning this here, you want this to be as small as possible, because when the margin of error is small, that means that your estimate of this unknown population value is much more precise. Okay? So again, a lower margin of error translates into a more precise estimate. A higher confidence level does not necessarily guarantee a more precise estimate. I'll demonstrate that later on, that you cannot, when you increase your confidence level, assuming other things unchanged, what that actually does is it makes your margin of error larger. Okay, so let's focus on this formula here. I will explain this, the three things that affect the margin of error. The first item that you see in this formula, the Z, this is your confidence level, okay? Sigma is the population variability. And then N, as we know, is the sample size. So if you observe here in this formula, if you want an estimate of an unknown population parameter, such as the mean, if you want the margin of error to be smaller, what sample size would you need? Smaller or larger?
Larger.
Larger, that's right. So as sample size increases, the denominator in this formula goes up, which in turn will make your margin of error smaller. Okay, the smaller the sample size leads to a higher margin of error. Next, how about the standard deviation of a population, which translates into, the diversity of a population. When I say diversity, I'm not talking about necessarily people, but rather the homogeneity or heterogeneity of the elements of a population. So if you are drawing your sample from a population that is fairly homogeneous, okay, meaning the elements of that population are fairly the same, right? Assuming Z and N held constant. When you have a population that has low variability, okay, what is its effect on the margin of error compared to a population that is fairly homogeneous, meaning when the standard deviation is higher? What is the effect of a, in terms of the margin of error in the precision of your estimate when you are selecting from a population who's fairly homogeneous versus a population that is heterogeneous, meaning very diverse? What is the effect on the margin of error?
All right, so I'm going to say that the more variability, the larger your margin of error, and vice versa.
All right, good. So the more variability there is in a population, the more difficult it is, the less precise your estimate will be, because the margin of error will be larger. Okay, thank you, Doug. Okay, so now that I've explained this too, how about the confidence level? All right, I said earlier that a higher confidence level does not necessarily translate into a more precise estimate. Okay, let me explain that concept in a new worksheet. Okay, so I'm going to recreate the formula for the margin of error. X, you have Z sigma over the square root of n. Okay, so let me explain this, what the Z is. The Z is based on the confidence level that you want to attach to your interval estimate. Okay. And typically the confidence level could range from, say, 90%, 95%, 99%. And these are the typical confidence levels. So let's say that you are trying to compute a, say, 95% confidence interval for the mean, an unknown population mean. All right. What this means is that when you compute X bar, the formula, first of all, is this: X bar plus or minus Z times sigma over the square root of n. Okay? So here's what we're trying to, going to convert the 95% into a z-score. What this means is this, that when you compute the lower limit, meaning X bar minus whatever this margin of error is, that this point here, X bar minus E, is what is known as the, now I'm going to use, let me clean this up a little bit so it doesn't look like an equal sign. X minus E. All right, now this is what we call as the lower confidence limit. I just added this one letter there, that means lower. When we add the margin of error to X bar, we obtain what is known as, this is known as the upper confidence limit. This 95% that you're seeing here is actually the area bounded by the upper limit and the lower confidence limit.
Renee,
Yes?
you mean on the upper limit, it's X bar plus
Oh,
E.
thank you. So are we clear so far what this 95% represents, this one here, in terms of where it is in the distribution? All right. So the next thing we need to do is we want to convert this 95% into a z-score. All right. What is the z corresponding to a 95% confidence limit? This is something that we covered previously in the last two chapters, right? So if the area between LCL and UCL is 95%, we want to find the z-score associated with this point here and that point. Okay, can anybody tell me what, how we can obtain the z-score over here and over here? The z-scores will be the same, except that this will be a negative z-score. This will be a positive z-score. Can anybody tell me how we can do this? How we can obtain the z-score associated with this point here?
Could you divide 95% in half, and that would give you,
Okay.
you could use inverse norm after you had how much you needed on each side of the mean.
Okay,
I think
so
you
if you
could do it
do,
that way.
are you dividing 95% by 2?
Yeah, that's correct.
Okay, so if you divide 95% by 2, that will give you an area of what? 0.475?
Yeah, that's right.
Um, 0.475. So where is 0.475 in this distribution?
Would it be the upper limit?
The what? The upper limit over here?
Yes.
From where?
From the mean over to the upper limit.
Okay, yep, that too is 0.475. So this will be point, let me see, point, 0.475. And this also will be 0.475, right? Either side of the mean will be 0.475. So how do we get to Z? Using the Excel function. This is the function. Okay. So what's the probability that I will put inside this function?
Would it be 0.025?
0.025, correct. All right, so we will not be using the 0.475, but rather the tail end area. Oops. Okay, so back here, here's the z-score, but it's really not 2. So make sure we need to change the decimals to 2 or 3. So the z-score associated with the lower z-score associated with a 95% confidence interval is 1.96 negative. Now, I said that the z-scores will be the same, right? This will be the same as this one, except that one is negative and the other is positive. You can confirm that by creating, again, using a function, the same function. This time, norm.s.dist point, let's see, 975. Hopefully I added my 0.475, yeah, 0.475 plus 5 correctly. Too few arguments because I used the wrong function. And there you go. So this is the more precise z-score, okay? Are we good so far in terms of converting a z-score, such a confidence level in terms of a z-score?
Yes.
Can you go over the calculation of how you went from 95%? There was a division and then we got to the 0.475.
Right. Somebody said that, we divide 0.95 by 2. So when we divided 0.95 by 2, we get 0.475. And the 0.475 is really the area from, say, this point to the middle point, and from this point to the middle point. So if you want to find the z-score such that the area between the middle and the lower limit, what we need to do is to obtain the area, the tail end area. If we were using the norms, norm.s.in function, okay?
Thank you.
All right, so just compute 1, and knowing that the distribution of the normal distribution is symmetrical, you will know that this point here will have the same z-score, except that it'll be positive. All right? Now,
Is there a way to-
sure.
Can you-
Go ahead.
Oh, can you calculate the z-score without the function? I mean, is there another way to do that?
You can use the table.
Table.
So yeah, table of random numbers. Oh, not the table of random numbers. Or you can use this table here down at the bottom.
Oh, okay.
But then you'll be doing some estimation. So it's probably best if you just know how to use the function to convert an area in the distribution into a z-score.
Okay, thank you.
All right, thanks, Christopher. Okay, so let's see. How about on your own? I'll give you maybe a minute to do this. Find the z-score when you want to compute a 99% confidence interval for the mean. So find the z-score. Okay, you can do some sort of visualization here. What's happening here is that when you increase the area from 95 to 99, what will happen to these bars here? This one and this one. Will they go inside, or will they go outwards?
They're going to move to the outside.
Exactly. So they'll move this way, right? So what that tells you is that the z-score associated with the 99% confidence level will be a number that is more negative than this and more positive than this. Okay? So try doing it on your own and give me the z-score associated with the 99% confidence interval. So here we had plus or minus 1.96. I'm rounding up. Okay, so try finding the z-score associated with, well, let's do the 90% also. With the 90%, from 95 to 90% will go inward, right? So does anybody have the z-score for 99%?
I've got that at 2.5758.
Okay, 2.575.
58, or I guess you could do 576 if you round.
Hold on, we'll just say, how about that? Okay, confirm?
That's what I got too.
Yep.
Okay, good, thanks. How about 90%? Confidence interval, the confidence level 90%. What z-score does that generate?
I got 1.645.
All right, 1.645 plus or minus. Okay. So I said earlier that increasing the confidence level does not necessarily translate into a more precise estimate. In fact, when you increase your confidence level, when sigma and n are held constant, when you increase your margin of, when you increase your confidence level, what it does is it increases the margin of error. Okay? So are we clear here? All right. So I think we're now ready to do some problem solving because of the most, I think, most difficult part, no, I wouldn't say difficult really, most challenging part that students find is in this converting a confidence level into z-scores. Okay, so let's look at, let me pick one from your textbook. Okay, so here's a simple problem. Let me add this. All right, this is problem number 1. All right, so the problem is a sample of 49 observations is taken from a normal population. Okay, so right off the bat, they're saying that the sample is coming from a normal population with a standard deviation of 10. The sample mean is 55. Determine the, I'm going to change this, instead of, you know, what we already know, the 90, 95, 96, and 90 and 99. I'm going to change this to 98% confidence interval for the population mean. Okay, so simple question, simple problem. Now, the first thing we need to do is to perhaps identify the given information in the problem, like 49. What is the symbol that we're going to use this in here? We know it's a sample, right? So what is the symbol for sample?
N.
Which one? Uppercase or lowercase?
Lowercase.
Lowercase, okay? Good. How about this? We know it's a standard deviation, but which kind?
Sample with an S.
It says, all right, now, note here that it says taken from a normal population with a standard deviation of 10. So which, you know, which is this describing? Is it the population or is it describing the sample?
I want to say it's the population.
Why, Chris?
Well, just the way it's worded.
Right.
It's taken from a normal population with a standard deviation of 10.
Correct. So it's the standard deviation is a normal population with a standard deviation of 10. So by, you know, by this phrase, this is sigma. Okay. The sample mean is 55. What is this?
X bar.
All right. Determine the 98% confidence for the population mean. So we are being asked to do this. Compute the 95% confidence interval. Not 95. Sorry. 98% confidence interval for mu. So if we draw the distribution, that will be, you know, x bar minus e, x bar plus e. The area between these two is 0.98. So give me the z-score associated with this and that point, these 2 points. All right, so this is the z-score for a 98% confidence level. Now we compute the confidence limits using the formula that we see in this flowchart. Okay, so this is the formula that we're going to use. So this one says x bar plus z times sigma over the square root of n. And this one says X bar, oops, sorry. This one is not plus, but rather minus. X bar plus Z times sigma over the square root of n. And substituting the given information in the problem, X bar is 55, right? Over here. Minus Z is 2.3264. I'm just rounding up here. Times sigma of 10 divided by the square root of sample size 49. Okay, and then this would be 55 plus 2.3264 times 10 over the square root of 49. 55 minus 55 plus. So from this point on, I'm just going to use Excel to compute, to do the computation for me, computing the margin of error. Okay, so the margin of error is equal to 2.3264 times, and close parenthesis, 10 divided by the square root of 49. Close parenthesis. All right, so essentially I just translated this handwritten numbers into an Excel formula so that you can see the calculation. And here's the margin of error. Let's increase the decimals to say 3, so that should be good. And since the margin of error, or the distance between the mean and the lower limit and the mean and the upper limit, the distance is equidistant, then I'm just going to use, I'm just going to say this is equal to whatever that number is. Okay. Are we clear so far? All right. So the lower limit is computed as equals 55 minus 3 point whatever this is in that cell. That's the lower limit. And the upper limit is equal to 55 plus the margin of error. Okay? So together, this number and this number, they comprise the limits. So we would say, and here's now how we interpret these two numbers. We will say that we will be, or we are 98% confident that the interval (51.68) and 58.32 contains the actual population mean. U. All right. Is that clear in terms of the interpretation of the resulting numbers? Okay. So are we clear in this manual way of computing the confidence intervals? All right, good. So let's take a 5-minute break. And then when we come back, we will redo this problem using the template. Okay, so that we don't have to do all these manual calculations. All right. So any questions on this problem 1, which we solved by hand?
I have a question about that flow chart. I was looking
Sure.
through chapter 9 and I couldn't find it in the book.
A what?
The flow chart that you had,
Uh-huh.
is it actually in the book or is this just a file on Moodle?
No, it's a file in Moodle because this, all these summaries are my own creation based on my summary of the chapter. So you will find this in the Excel file in week 3.
And David, also in the course outline notes that he has in Moodle, it's on page 39 and 40 of that course outline.
Thank you.
Thanks, Doug. All right, so let's rework exercise 9.1, and let's see how we can accomplish the same numbers and see if these numbers are correct or accurate using the template. Okay. So here we go. So far, we've gone through this set of templates from the last two weeks. Now, this week, we're talking about chapter 9, which focuses on confidence intervals for one population. Okay, so we're simply talking about one group. The 3 sets of templates here are the confidence interval for the mean, confidence interval for the proportion, and confidence interval for the variance. All right, so chapter 9 only deals with the mean and proportion. This one is covered in a different chapter, which is the chi-squared chapter, which we will be covering towards the end of this term. So for the problem 1, we computed the confidence interval for a population mean using the Z distribution. So let's look at what the template is. All right, so here you go. You input information that is provided in the problem. So this is where I said that it is important that when you are reading a problem, that you're able to identify the information, what's given, and the appropriate symbol, as well as what that number represents. So that when you are filling in information in templates, you know exactly what to put in these cells. All right? So what was the sample mean from the problem? What was the number?
Was it 49?
No, that was the sample size.
Sample size, okay.
So this is 55, right? The standard deviation of the population? Wasn't that 10? The sample size, that's 49. And the significance level. So this is the significance level. Iridian mentioned this earlier, is actually the significance level is the difference between the confidence level subtracted from 1. So 1 minus 0.98 is 0.02. So this one is also known as the significance level.
And you said that's 1 minus the confidence interval?
Correct. Confidence level. Not, So 1 minus the confidence level is equal to alpha. Okay? And that's also the sum of the tail ends. All right, so this should be 0.02. Okay, so here's the confidence interval that we computed, okay, so which confirms our numbers. That number there and number there is consistent with what we have over here. We good? Maybe let's do one more sample from the textbook. Problem 2 from your textbook. So here is a sample of 81 observations. Is taken from a normal population with a standard deviation of 5. The sample mean is 40. Determine the 94% confidence interval for the population mean. So I'm going to let you do this on your own. I'll give you 5 minutes to do the same problem. You can use the manual way, or you can use the template. And we will confirm, for those of you that do the manual way, we will compare the answer using the template. All right, so let's look at this problem. What is 81 in this problem? And what is its symbol?
81 is n, and it's the little n.
Okay, and sample size, right? Good. How about 5? What is 5?
Sigma.
Sigma, good. I'm spelling it out because I don't have the, I can't put the symbol there, but you know what I mean, right? Sigma, this is the population standard deviation. Good. Uh, 40. What is 40?
Would that be X bar?
Uh-huh. That's the sample mean, correct. All right, so how about the Z value for 94%? Meaning, if we drew the distribution, that the area between the upper limit and the lower limit is 0.94. Okay. So what is the Z-score corresponding to that point as well as that point? Did anybody get that?
So for the z-score, it's 1.880. Let's round up to 8.
1.880.
08.
08, okay. All right, let's confirm that. So the z-score will be, we can use the norm.s.inv, and then the probability is point what?
97.
0.7. Why did you use 0.7?
I said 0.97.
Oh, 0.97. Okay. So if you do 0.97, what you're actually obtaining is the area from the upper tail over here. What you're actually doing is, let's do that, 0.97. That's one way. All right. So what Iridian is doing is finding the area, oops, I didn't mean to use that kind of pen.
That is pretty.
0.97, and this would be 0.03. Okay, so either one. So this 1.88 is actually the positive side. This one would be equals norm.s.inv 0.03. It should be the same. All right, that's that. Okay, so that's good. Now, let's compute the lower control limit. So the formula that we will be using is this. 94% CI for mu is equal to x bar plus or minus z times sigma over the square root of n. So which is, you have 40 plus or minus z, which is 1.881, we can round it up, times sigma 5 over the square root of 40. So that's the formula for computing the upper and lower confidence limit. So here I'm just going to type a formula that says equals 40 plus 1.881 times 5 divided by the square root of
81.
40. Oh, thank you. 81. All right. So is this the lower control limit, lower confidence limit that you guys obtained?
No, I got that for the upper.
That's the, okay, I added the, all right. So for this one, I'm just going to copy that, but change this to A minus. Oh. What is happening there? Doug is laughing at me. All right. We're good? Now,
Yes.
how about the margin of error? What is the margin of error? You can solve that by hand using this, or how about using this information that we have here? How can we compute that margin of error?
40 minus one of them.
Okay, 41 minus 0.45 minus 38.955. That gives us the distance between the upper and lower limits, right?
And wouldn't we divide that by 2 to say that the margin of error is plus or minus what turned out to be 1.045?
That's correct. All right, so that's the margin of error. Good. And let's resolve this problem using the template. Same template, the z distribution. What was the sample mean? Was this 40? And the standard deviation was 5, right? Sample size was 81. And the significance level 0.04. Okay, so here's what we computed.
Isn't it 0.06?
Oh, thank you. Thank you. So there's the numbers that we used. So these numbers now match that. These numbers match. So for this problem, let's just do the template. Okay, identify the distribution that is appropriate and use the template. A recent survey of 50 executives who were laid off during a recent recession revealed it took a mean of 26 weeks for them to find another position. The standard deviation of the sample was 6.2, and we are to construct a 95% confidence interval for the population mean. Is it reasonable that the population mean is 28 weeks? We are to justify our answer. All right, so compared to the previous two problems, where we simply computed the confidence intervals. In chapter 34, we are to make sense of the interval that we compute, and that is, we will answer the question whether it is reasonable that the population mean is 28 weeks. Okay, we will justify our answer why we say it is or it is not. But just like before, we'll go back to, again, trying to answer this basic question, starting with what is the parameter of interest, meaning what is the population parameter that is being estimated. What is it that we want to estimate? Is it population mean? Is it population proportion? Is it population standard deviation, or is it population variance?
Population mean.
Okay, good. Or mu, all right. What is the variable of interest? We will define X again. What is the definition of X in this problem?
The number of weeks it took to find a new job.
There you go. Number of weeks to find another position. Okay. What is the classification of X? Is it discrete or continuous?
Continuous.
Okay. What is the probability distribution of X? Is it stated in the problem?
Is it the 95%?
No, that's a confidence interval. So when it asks for the distribution of X, what is the shape? If you were to, draw the shape of the distribution of X, what will be its shape?
So it doesn't completely say, but it would be normally distributed
Okay.
between the sample.
So not stated, correct. But since n, the sample size, is large, how large is sample size?
It's larger than 30 because it also didn't say that it was.
Okay, so what is n in this problem?
50.
50, we will say that the distribution of X bar will be normal, right? This is by the central limit theorem. All right. Now, let's identify the given information. N, we said was 50. How about 26? What's 26 here? What's the symbol for 26?
X bar.
Mm-hmm. And how about 6.2?
Sigma.
Read the sentence again.
Oh, of the sample. I see.
All right. Yeah. So yeah, sometimes just be careful when you read the statement so that you know whether a standard deviation is a sample or sigma. All right. And we want to find the 95% confidence interval for, as we said, we're trying to estimate mu for the mean. Okay. Now, as far as this is concerned, are we going to use the Z or the T distribution? What do you think? If you're not sure, follow this flow chart. Okay, population mean. Is the population sigma a standard deviation known? The answer is no. Then here's where you can say if sigma is not known. Okay, over here. No. Is the sample size large? The answer is yes, right? Because the sample size was like 50, wasn't it? Yep, 50. So because of this, we, by virtue of the central limit theorem, we can use, I'm stressing the word can here, you can use the Z distribution, the Z-test. But if you use the t-distribution, that will be correct as well. All right? Are we clear there? We will solve this problem using both distributions, and we'll see how close the answer will be. All right. So since in this problem, since n is large, we can or may use the Z distribution. You will be correct also if you use the t distribution. Okay, so first let's use the t distribution in solving this problem. Okay, please remember these numbers, okay? So when I input these into the template, we'll have it correctly. So I'm going to compute the mean, the confidence interval for the mean, using the t distribution. Okay, what's the sample mean?
26.
Okay. Sample standard deviation?
6.2.
6.2, thank you. Sample size that I can remember, I think 50.
Mm-hmm.
And then significance level 0.05,
0.5.
right? Okay. So that's here's the lower confidence limit, upper confidence limit. Okay, so that's, here are the answers, or at least the confidence limit. Okay, let's solve this same problem, but this time we will use the Z distribution. Okay, sample mean. still forgot what that was.
26.
26, thank you. Standard deviation, was it 6.2?
6.2.
Sample size 50,
Yeah.
0.05, right?
Yeah.
Okay. Okay, so they're different, but they're slightly different. Oops. Oops. So in this case, you can use either this number or that number. Are we clear so far?
I actually have a quick question.
Sure.
So, does it matter if it's a sample mean or a population mean?
What do you mean? In this case, it matters to know which one is which, because in this case, what we're trying to do is we are trying to estimate, come on. We are trying to estimate this one using X bar as its point estimate.
Okay, thank you.
Okay. All right. So remember that this is the unknown.
Okay, can I insert something there real quick?
Go ahead.
Is it Shania? So,
Yeah, it's Shania.
okay, so part of what I think what if the question were to have given the population mean instead? Do you understand what you would do then?
No.
Okay, so that's where he was talking about before, where they're almost the same. So you would just substitute the population mean into this template as the sample mean.
Oh, okay. Thank you.
Let me, now, hold on. You don't know. You mean you use the sample standard deviation in lieu of the population standard deviation. Right? I mean, is it, in this case, since I'm using the distribution, remember that 6.2 was a sample standard deviation. So when the sample size is larger than 30, because we are using the central limit theorem, what we're doing is we are substituting S for sigma in here. So that we can use this this template.
So then what would you do if in the, say this exact same question, but it gave us the population mean instead of the sample mean?
Oh, you can, because I mean, if the population mean is given, then there's no need to compute a confidence interval.
Okay.
Right? Because the whole purpose, really the whole purpose of confidence interval estimation is we're trying to figure out what this unknown population mean is. And in trying to estimate this, we are using X bar. So there is no place in either in the formula, X bar minus Z plus or minus Z times sigma over square root of n. There's really no place for mu there, because what we're trying to do is to estimate this using this formula. Does that make sense?
Yep. Okay. So Shania, hopefully I didn't throw you off there.
It's okay.
All right. Okay. So are we clear here so far? We were able to compute the interval estimate, but I said earlier that there's really something that we need to make sense of based on this interval estimate. The question is it reasonable that the population mean is 28? Yes or no?
No.
Why not? Shania?
Oh, that was me, Stella.
Oh,
But
Stella, sorry.
because the 28 weeks is not in between the 24 and the 27, so it's not reasonable for the population mean to be in between them.
That's correct. All right. So this kind of will lead us into the hypothesis testing later on, is that if somebody says, hey, you know what, the actual mean is 28, if somebody claims that to be true, then you say, hey, that is not reasonable, because the probability that 28, is, well, the confidence interval does not contain this, hypothesized number, if you will. So the answer to this question is no. And as Stella reasoned, this interval here does not contain this value.